have Lauren Norman. So you might remember Lauren from last year. She's been doing a lot of interesting work in the watershed for a number of years. Last year she was speaking on restoration site selection and design and how to assess restoration efforts in Baba Kamari and predicting the effects of climate change and land use change in that area. So she is a research physical scientist at US Geological Survey, we were just talking about them, where she has worked since 1998. Dr. Norman received her PhD in watershed management from the University of Arizona, where she minored in remote sensing and spatial analysis, and that was in 2005. Her research uses remotely sensed imagery and other geospatial data and complex models to predict the fate of non-point source pollutants and identify their processes, consider potential growth scenarios, and identify watershed processes. So thank you. Bye.
Thank you. So I was asked to talk a little bit today about runoff and how different things on the landscape might impact runoff and subsequent erosion. So I tried to focus my talk about that type of thing in the Cienega watershed, although I haven't done too much modeling there yet myself. Some of the research that I'm presenting is from some other colleagues at the USGS, so I've got their names on there. So to start off, obviously some of the things that impact runoff include climatic controls, like temperatures and precipitation, which we have high temperatures here and little precipitation. That increases your likelihood of high runoff, and the high temperatures increase your ET. So watershed vulnerability increases with climate changes like those, but there's also the potential to impact runoff and subsequent erosion via land use management. And so some of the things that have impacted watersheds' vulnerability to high runoff and erosion include grazing, logging, channelization, draining of wetlands, the removal of beavers, groundwater pumping, and fire suppression. And I'm going to talk about some of those things and management applications that I've seen that have reversed those processes as well. I'm a watershed modeler, so everything I do, I kind of visualize in this model. And when I first started at the U of A, a professor said to me that everything was a model. And when you're asleep at night and you get up to go to the bathroom, you have a model in your head of the path to get to the bathroom. And sometimes you get to the bathroom without bumping into the bed, and sometimes you do bump into the bed a little bit. But that's kind of how I visualize the watershed models that I apply. You know, this is kind of, you know, how you would describe things in the middle of the night when you get up. So this is the hydrologic model, and this is the budget that I'm working with and I'm going to present around today. And Jean Marie's already done an incredible job talking about recharge. So the precipitation falls from the sky, it hits trees, there's processes of interception, it runs off, there's processes of direct runoff and base flow runoff that I'm going to describe further later. They can infiltrate the soils if possible, and then potentially recharge the aquifer. There's also the processes of evapotranspiration. So it can evaporate from the surface because of high temperatures, or the trees and plants can transpire and use up some of that water as well. So what comes up, it goes around, and there's no new water. So it's just a matter of where's the water going when it comes from the sky. So I was asked by Pima County Flood Regional District Control or something like that to look at the potential impacts to doing some restoration in the upper watershed, and how different areas might change erosion problems that they were seeing in the preserve. So I looked at the larger model, and I created a different kind of watershed map based on some of the locations that they were interested in looking at. And here's a picture that my student Natalie Wilson took in the reserve. You can see the trees terracing and the erosion happening at the reserve. And so they were interested to see what were the peak flows. And so I ended up doing kind of a mock run of a watershed model to look at areas that might have higher runoff and higher sediment yield or recharge potential in the watershed. And a lot of times people get stuck on one model, and what is, this model is the only model, and as a person that applies models for a living, I found that there's a lot of different ways to skin a cat. You can do all different types of models and end up with very similar results. And so I applied one model, but I tried to compare some of the different models that other researchers have done in this watershed so that you can see that despite the fact that I'm using one model, which I ended up using the SWOT model, there's many different ways to do the same kind of thing depending on what your needs are and what your tools are at hand. So the SWOT model was developed by the USDA. It's the Soil Water Assessment Tool, SWOT. I find it to be very user-friendly. It's a GIS package that is convenient to use and has been tested widely in the United States and internationally, and it's free. So it comes from the USDA and is very robust package. And the SWOT hydrology looks at the watershed using the same water hydrological cycle that I was presenting earlier. So you've got the same circle happening where you've got daily inputs of temperature and precipitation. You have a soils layer that you can consider, the topography, digital elevation models, a land use map that you can derive different curve numbers from. And then you can also create management applications that may impact that hydrological cycle. And the outputs then are hydrological budgets, sediment yield, and you can also derive nutrient and pesticide information, which I did not do for this watershed. But it's a way to model things running through the watershed and the surface. So there's an attenuation can be accounted for. It's very nice. So here's the elevation model that I used for the watershed. At the time I was using a 10-meter DEM. Since we've got some higher resolution data sets for different areas of the model that I'd like to stitch together and redo. But so the 10-meter DEM, and I divided that into 4 different groups looking at different slopes. The land use map is the regular NLCD the USGS produces for the country, and that is fed into the SWOT model and reclassed based on the different land uses, including wetlands, urban, agricultural, and then the soils map from the USDA StatsGo database. So this is actually mostly SERGO, so a higher resolution soils classifications. There are a bunch of background models, kind of tried and true hydrology algorithms that have been developed through the years that work behind the scenes in the SWOT model. So to develop estimates of surface runoff, you can choose different models, the curve number being one of them, and those are listed there. As I mentioned before, I re-subdivided the watershed based on information that was provided to me from the county and then from some colleagues that had been doing some research. The watershed is subdivided based on elevation. Really, the boundary depends on where the mountain ridges are. So you can identify outlets from the watershed where everything is running off to. And I chose the GS's gauge at Centeno to use there. And I also identified some outlets where the county had been interested in maybe doing some inland fee restoration. So those are those pink spots. Then in speaking with Ron Tiller and Andrew Saliwan, who had expressed interest in the Cienegas at Cienega Creek, I also chose locations around identified Cienegas as outlets, so we could look at the direct impacts at those Cienegas when doing the model. And lastly, I used the gauges so that I could use the hydrographs from the gauges. So these are all the different points, the different outlets that were put into the model, and these are all the different sub-watersheds that were then created based on our areas of interest, the points in the county and the Cienegas. So 22 outlets. At the locations of the GS gauges, and Jean Marie showed one, but these are hydrographs of the different gauges through the years and trends through time. And one gauge has been active since 1959. So I chose that oldest gauge to consider in my model as the calibration point. So in calibrating the water balance, it involves looking at what the precipitation inputs are, what are the runoff, what are the different hydrological cycle. And in this case, I ran a hypothetical simulation for 21 years with the warm-up of 5. And the HRUs are the hydrological units that were subdivided within the 22 watersheds. So there was 85 different hydrological units with different land use, different soils, different slopes that then could be considered by the model. I did it on a monthly time step, and precipitation was simulated. So we do have real-time precipitation that I consider putting in the future. But just out of the box, this is what the hydrologic budget looks like in the Cienega Creek. So with precipitation 419 millimeters, and then ET accounting for about 75, maybe a little bit more percent of that, then you have about 25% left over to work with on the ground. So you can have that as runoff, and the model simulates 25 millimeters of that getting shed as surface runoff, or it could be percolated into the soils and move through the ground in lateral flow, so base flow elements. And that's something that we're finding, based on model results, isn't really occurring in arid lands. And so most recently, we had a publication with Dr. Meixner and a student named Rawati Naraula, who calibrated the model at this location for a larger watershed, the Santa Cruz, and found that when you remove the lateral flow from the model, then it predicts what's happening at the gauges. So the model was able to tell us that this is the feature that is missing from our picture here. So that's something that I'll get back to in the next couple slides. So here is an example, the gauge that I suggested we'll be calibrating to for this model, and you can see the blue is the simulated runoff at that location. The red is the observed runoff at that location. And I think that the red line is representing that direct surface runoff, and the blue line is taking into account that non-existent base flow that is not occurring there. And so the question then becomes, how can we increase base flow in arid lands? And that's something that I've been looking at Valera Austin's property in the Chiricahuas, where she's been able to increase base flow by 28% using check dams. So there's the calibrating the water balance and calibrating the hydrograph. And these are two different things to consider in arid lands and using models. So I used this SWOT model in the runoff. I used the SCS, Soil Conservation Service curve number, to calculate runoff. And despite the fact that I didn't calibrate the model, I did look at the peaks, and I see that it's representing that direct runoff. So here's areas that the model is predicting would have higher areas of direct runoff. This area around Empire Ranch at the Cienega Creek gauge near Sonoita. That watershed looks to be the area that has the highest runoff. Then the areas on the west side and southeast side of the watershed. So where there is mountains also in the watershed, there seems to be some runoff coming from there. In a similar and much larger study, the Flints in California, Lori and Alan Flint, published a regional analysis of groundwater recharge, where they created maps looking at both runoff and recharge in one area that they focused in on was the Cienega Creek watershed. So that is this little area next to the San Pedro. And on one side is the runoff, and on the other is the recharge. Bless you. So I took those maps and put them into my little watershed boundaries so I could better see where the areas of recharge and runoff were based on the Flint's research. And then I went ahead and overlaid the boundaries from the SWOT model with what they had done and see that they're similar. So they didn't use soils data the way that we had, but they had used geologic inputs. And so the results are very similar in the areas of recharge or runoff. Again, the high values there and here, then up into the mountains. In the SWOT model, they use a modified soil loss equation that takes into consideration runoff from the watershed versus precipitation. And so the runoff is used to push sediment through the system. And in this application, the runoff showed that there was some high sediment potential here in the Santa Ritas over by where the proposed Rosemont site is, and this is based on that runoff map. So it would be interesting to look at more sediment yield representations that better represented the potential for precipitation, as the lateral flow was not represented in this model. Phil Heilman did a look at some of the sediment yields in the upper watershed to Cienega Creek using a couple different models than we had used, and were able to do some scenario analysis that I'd like to try to mimic as well, where they found that by increasing your conservation and rangeland management, you could decrease your sediment yields from these locations. And so some of the numbers between 4 and 33% decreased in sediment yield. And so these are the potential impacts of monitoring and holding runoff. I'm going to talk really quick about the recharge that we got from the model, and just wanted to show the relationship to both what Jean Marie had presented, the Osterkamp map from 1973. So Wade was out here when I was 1 year old doing this exact same thing. And some of the stuff that they, and I took that map, so Jean Marie had helped digitize, and I just overlaid that map with the watershed to look at the boundaries and the aquifer and the model that I had run to see how the recharge estimates from that compared with the recharge estimates. And again, this high area around the Cienegas. And I couldn't help but overlay then the recharge stuff from the Flints. And everybody agrees there's not a lot of recharge happening here, here, and here, but maybe the mountain fronts being the area to focus in on to try to increase recharge in the basin. This is a little simulation that James Caligari had shown me. I don't know how to, there. So hopefully it will run. Oh, QuickTime's not available. Well, it's a very nice little movie, you can imagine. It opens up, what happens is water it comes up with this line, and as it meets the surface, it expresses. So when the groundwater meets these low points, you have these springs, and the water then is made available. So the potential to increase where the groundwater recharge is happening then can be expressed in the surface. And again, this is a map that Wade had worked with some students on in the Sonoita Plains that shows the potential water depth to water. So in this area around the Cienegas, you have a 0 to 10 meter depth to water, and then on the
this? I don't understand that now. Like the location of something?
Yeah, there's Sonoita.
Oh, okay.
And there's Elgin.
Okay.
Here's the Empire Ranch area in okay. Yeah. So that's that alluvium area that Jean Marie had shown, where there might be the potential clay deposits, and the surface water is closer to the surface. Groundwater is closer to the surface. At those locations, we had investigated with Natalie Wilson's thesis the potential to look at Cienega changes through time, and that was working with Andrew Saliman and Ron Tiller to look at satellite imagery through time to see how the Cienegas might be changing and if they were indicator of surface water availability at the Cienegas. And basically what we found is that the Cienegas weren't really showing trends through time that were related to the drought, but rather to management. So this is kind of a steady state at this one example. But at locations that had previously been agricultural fields that had been managed to put water into, they were no longer being managed to put water into, and so they were drying up. But so that was an example. There's always the potential for error in any of the models that I might have presented and talked about and thought about in my head in the middle of the night. So there's uncertainty in relationship to what I put into the model and also the data that was used to model. And a lot of these different models were created not for arid lands, and so they have to be modified for the environment. And any of the inputs then could be modified as well. But I guess my take-home point about how different factors can impact runoff and erosion is that as precipitation happens, you get direct runoff, and the more precipitation you get, then percolation into the groundwater. More precipitation, you can then create base flow. And then if you take that direct runoff away, though, the water still has to occur in that location. So if you dam it up, if you put check dams in, that water is still occurring at that location, and then you can increase your percolation in your groundwater supply, bring it up to the surface, and have that potential base flow that would occur as runoff in the long run. And that is what I would say you can do. You don't have control over the meteorological factors that impact runoff, but intensity, amount, duration. So the drought that we're in, the El Niño that we might have, but you can impact the land use. You can put check dams in, you can put one rock dams in. We've got a great project going on at the Babo Kamari right now where we're experimenting with that. Chloe's got a project, Chloe Fandel, at the university to look at the impacts to soil moisture at that location. And this vegetation enhancement, planting, slowing down the runoff and increasing your base flow being in this beautiful picture, I'll leave off that Andrew Saliman shared with me. So,
I just have a question about terms. They use the term base flow, and are you using it to refer to the lateral flow that's in the soil? Because I use base flow to refer to where the groundwater tables intersect the surface water and you've got groundwater discharge. That's the lateral.
Yeah, so it includes the lateral flow. And so, yeah, that would be the component that I think is missing from the landscape right now is the water doesn't have long enough time to build up in the soils and create a wetted surface that then, when new rain comes in, could then slowly run off. Rather, instead, it's getting shed from the landscape immediately, and so the soils remain dry through time.
Is that more of a typical characteristic of desert soils as opposed to like the thicker mountain duff, the forest duff and such?
I do think that the soil types are indicative to that, but I also think that the climate impacts that as well. So different soil types would react differently, but if there's not enough rain, a lot of soils would be scared to pick up
So on your kind of watershed level, you said when you did the simulation, you had to take out the lateral runoff component. I mean, basically at a watershed scale, you're not seeing enough kind of storage, water going into soil storage that can then flow out as base flow to affect the results. But the promising part of what you said, if I'm understanding it correctly, is that, you know, like in some of these Cienegas in the Empire Gulch area or La Cienegas in general, I mean, a lot of those aren't tied necessarily to groundwater. There has been good land management. Water is going into this lateral storage, and it's something that we can all affect. Is that
Yes,
correct?
yes, and increase the potential.
Yeah, that's a very helpful thing in this day and age. I mean, wow.
Yeah, I hope this makes sense. I'm just curious about what kind of studies have been done on micro-channelization, you know, because one of the things I've observed over the years is the depths of washes. You look at the Santa Cruz, which once used to have outflow from the heavy runoff, which is now deeply channeled. Now, every time you get a rain, especially with our heavy rains, you get fast runoff, which creates channelization. And that just amplifies because each channel builds the further channel down, so eventually you've got a deep one.
Yeah, that's a really good point. And Julio Betancourt did his thesis looking at arroyo channeling in the Santa Cruz, and it's just been, you know, rampant. And one thing is that it's a cyclical process, is that more channels will create a higher flow, will create more channeling effects. So to kind of go in and jump in at those head cuts and put some kind of restoration device so that they stop doing that is really to arrest that process. Yeah.
All right, one more.
You know, I noticed that in your models you use Manning's equations sometimes to represent changes in the situation, helping model. And as a land manager with some open channel hydraulics experience, it seems like one thing that we maybe can key on is watershed roughness and channel roughness to basically attenuate flows and to create storage events out of high peak events, not like peak events. So like on Cienega Creek, a lot of it's straightened out and we've lost beaver. So I think some of that storage that we used to get in the shallow aquifer, the floodplain aquifer, we're losing out on because of some incision, lack beaver, and so on. It's channel straightening past incision events. So it seems like we could probably increase our resilience there.
I agree with that 100%. Yeah, the check dams do that kind of channel detention, but vegetation as well could serve to increase your roughness, as you're saying, and that would be obvious in the model too if I was to manipulate the surface. So that's a really good point.